Hello and welcome to lecture 22. This is our final lecture. Congratulations on making it all the way to the very end. This has been an exciting time for me. I really enjoyed recording these lectures, interacting with all of you throughout the entire quarter, answering your questions, asking you questions, and just getting to know you. Thank you so much for making this course such a great experience. I really am happy that I've got to meet all of you. And I'm going to see you hopefully around the department in other courses perhaps that I'm going to be teaching, and all the best for you and the fantastic holidays that you're going to have. I also wanted to take a moment to remind you to please fill out the CTAX. It's super important for me to know how well I'm doing, what I can improve, how to make this course even more useful for your successors in the future, and how can I make other courses that perhaps would use the same lightboard technique even more exciting and engaging and easier to follow to make your lives easier and more exciting, hopefully. So thanks a lot again, and with that I'm going to get to it. So now in this lecture 22 we're going to start talking about infinitesimal canonical transformations. Why do we need even more of these transformations? Well, you're going to see this is going to be pretty useful. So let us write down a vanilla transformation. So this vanilla transformation has two terms. This first term generates an identity transformation. However, that extra term is going to make a little bit of a change because epsilon is going to be a small parameter. So let us see how it works out. So the old p's are the partial of the generating function with respect to the old q's, and the new q's is the partial of the generating function with respect to the new p's. So that's what makes this vanilla transformation so popular. So let's compute what this and that is. So df to dqi will give us the pi, the new ones. And here we're going to get epsilon times the partial of g with respect to the old q's. So far so good. In this one, we're going to get qi's, just like before we said it's an identity transformation, plus we're going to get epsilon dg dpi's. And from here, we can express the new coordinates and momenta, the big p's and q's, as a function of the old one. So let's invert the second one for the little guy. Turns out that we can write this out in the following vector form that we used previously. Namely, we can write this transformation as delta eta, where eta is q and p, and we can say that the change in q's and p's, the difference, is going to be equal to epsilon times the Poisson bracket of eta itself with g. So how do we understand that? So we can understand that by writing down that this is equal to epsilon d eta over eta tilde j, remember j, times dj d eta. And because d eta over eta is going to be 1, what this gives us is epsilon times j, which is 0, 1, minus 1, 0, times dg dq and dg dp. And you can compare this to that and see that this indeed agrees. So if we write here delta q and delta q will be equal to epsilon times dg dp, which is precisely this. Except you will say, well, this is a big P, whereas that is a small p. But remember that this is at its core an identity transformation plus something that's very, very little. The epsilon is pretty small. So there is very little difference between the big P and a little p. That is precisely why we can do what we're doing and replace the big P with a little p, and therefore represent our transformation in this form. So when we are switching to this notation, then we are going to make functions become operators. And what we're doing here is we're changing the variables. So this is an active transformation. So let us take a look at a few examples. Suppose we take G to be H, the Hamiltonian. And then from here, we're going to get the delta eta is going to be equal to epsilon times the Poisson bracket of eta and H. And this is pretty similar to what we knew before. Namely, the equations of motion for eta are given by the Poisson bracket of eta with H, or from here we can write out that delta eta under the action of H will be delta t times the Poisson bracket of eta and H. So you can see there is a very clear parallel over here where all we did is we replaced the small parameter delta t with another small parameter epsilon. So what this means is that H generates the evolution in time. Momentum generates translation in space, and angular momentum generates rotation, of course in space, not in time. Let us now use this machinery to try and prove the Noether's theorem in part 2 of lecture 22. And I'm going to see you right there. Hello again, and welcome back to our final lecture of this course, part 2 of lecture 22. Now we are getting to talk about Noether's theorem. So Noether's theorem, we actually talked about it a little bit before, and it connects symmetries with conservation laws. So suppose that our Hamiltonian is going to be invariant under the transformation G. So that would mean that the Poisson bracket of H and G is equal to 0. Recall also that G dot is the Poisson bracket of G and H. So how can we prove this? Because we know how the coordinates change under the action of G, but how does H change under the action of G? Well, for that, let's connect the change of H in the change to a change in coordinates. Like this. So the Jacobian tells us the response of H in response to changes in coordinates. And then we can express delta eta, just like we see over there on the left. And we're going to get epsilon from the infinitesimal transformation times this term times j times dg d eta. And this looks just like a Poisson bracket. So what we found is that if H is symmetric with respect to G or under G, then G is conserved. For instance, because H generates a translation in time, if symmetry is present, so if H is not affected by translation in time, H itself is conserved. Momentum generates translation in space, and if there is symmetry, then the momentum will be conserved. Or mathematically, if the change of H under P is 0, then P dot will be equal to 0. For this, we're ready to move on to a Liouville theorem and adiabatic invariants and action angle variables. All of that is coming up at the end of lecture 22. See you there. Hello and welcome to part 3 of lecture 22. Here, as promised, we're going to start talking about Liouville theorem. You can read more on this in Landau and Lifshitz, Volume 1, Mechanics, Section 46 or Chapter 46 or 49, depending on the edition. So Landau and Lifshitz, Section 49 in 3rd edition. Or maybe 46. I think I used 2 different versions and I've gotten 2 different values. So look around in the contents. So last time we talked about infinitesimal transformations. And you're wondering, why do we need them? Well, this is why. So you can see that delta eta given by an infinitesimal canonical transformation is of course a canonical transformation, and that transformation is generated by function g or operator g acting on the coordinates. Similarly, Hamiltonian also acts on the coordinates and generates a canonical transformation in time, also a canonical transformation. So time evolution of a Hamiltonian system is a canonical transformation. So let us write it down more formally. Suppose that we're switching from the old coordinates to the new coordinates. So we're going from eta coordinates to psi coordinates, and the differentials are related by this Jacobian, which we can write out as we did before. We can denote it as we did before by matrix M ij. So one question we would be particularly interested in, because we're dealing with Liouville theorem, is what happens to the space of Q and P coordinates, or the phase space. In order for this transformation to be described by Hamiltonian, it needs to be a canonical transformation, and therefore matrix M needs to satisfy the canonical condition. So what we're going to get then is, on the right hand side, we're going to get the determinant of J, which is 1. On the left side, we're going to get the determinant of M, J, M transpose. And because the determinant of a product of matrices is the product of determinants, we're going to have two determinants of M and M transpose, which are the same. So we will have the square of determinant of M times the determinant of J. And here, what's important is that the determinant of J is unity, just like it is here. So as a result, we can conclude that the determinant of M is either a plus or minus unity. And that means that the phase space is conserved. One way of thinking about it is that the Jacobian between the new coordinates and the old coordinates as part of this canonical transformation is the Jacobian d psi over d eta. And the ratio of the volumes, the big V over the small v, is going to be the Jacobian of this transformation, or the Jacobian d psi d eta, which is precisely what we have computed. So what the phase space conservation means is that the phase space volume in little QPs and in big QPs is the same. So we can try and draw this visually as follows. So if we go from T to T plus delta T, and we had a phase space volume, which we will denote as gamma at time t. By the time we move to next time, delta t later, our phase space volume could have changed if we follow all the trajectories that are in the volume and compute the new phase space volume that is filled by the trajectory, by all the trajectories. And so what this statement tells us is that delta gamma will be 0. It's not going to be changing. Namely, the integral over dq's and dp's is going to be the same as it was before when we go to the new coordinates. Or in other words, if gamma is the integral and d gamma is the integrand of the phase space volume, what we're going to say is that the integral of d gamma is a constant. The phase space volume doesn't change, so delta gamma is actually 0. Which is really amazing. So let us now move on to the next part of our lecture, where we're going to start discussing the adiabatic invariants. See you there. Hello and welcome to part 4 of lecture 22. Where, as promised, we're talking about adiabatic invariants. So, what are the adiabatic invariants? Let us consider an example of a particle in a magnetic field. in fact a charged particle in a magnetic field. Actually, let's make the field blue. Somehow I feel like the magnetic field is blue. And here is our particle, which is going to be gyrating around the magnetic field lines. What we're going to show is that as this particle moves around the magnetic field and the strength of the magnetic field changes, as long as it changes slowly compared to the period of the particle, then this expression that I denote by I is going to be an adiabatic invariant. The square of the transverse momentum perpendicular to the magnetic fields divided by the magnetic field strength is going to be conserved to a really good accuracy, much better than anything else in the system. So let's try and see how to show that. Before I go there, I just wanted to get a refresher of what sort of properties of motion does a particle have as it flies around the magnetic field. So there are two things to keep in mind for a particle moving around in a uniform, let's consider uniform field for simplicity. Whatever momentum the particle has along the magnetic field lines, parallel momentum is going to be conserved because there are no forces acting along the magnetic field. The magnetic force, the Lorentz force, is perpendicular to the magnetic field. So if we have a particle that's going around, it's going to have a radius of an orbit, r, and it's going to have a transverse velocity v perpendicular, the velocity component perpendicular to the magnetic field. And what we can write down here is the force balance, that the centrifugal force is equal to the Lorentz force, or namely the charge of the particle times v perpendicular over c cross b. And because v perpendicular is perpendicular to b, we can rewrite this as simply a scalar product. So here, because we're interested in finding the gyro radius of a particle, the radius of this circular motion, we're going to plug it all in here. We will be able to cancel one of the v's throughout. And we're going to be able to solve for the gyro radius, which will be this, or in the relativistic case, we're going to have to add a Lorentz factor. So this will become gamma mv perpendicular c over qb, or equivalently p perpendicular c over qb, where p perpendicular is the relativistic momentum. It includes the gamma, the Lorentz factor. So coming back to our adiabatic invariant, this adiabatic invariant remains approximately constant. So this gives us really interesting physics that I would like to spend a few minutes over. So suppose that the particle moves from a region with rarefied field lines into a region where the field lines are becoming denser. Into that region. Will the particle actually be able to go there? That is the question. And what will happen to the speed of a particle? So there is a really interesting effect called mirroring, that the particle actually can't go there. This is what causes auroras at the North Pole, when the particles actually getting stuck. They cannot go too close to the Earth's surface, and so they gyrate back and forth along the magnetic field lines until they emit all their energy. And magnetic field, precisely because of that reason, protects us from the cosmic rays, from the charged relativistic particles. So let's look at the energy conservation of a particle like that. The square of the energy will be the sum of the parallel and perpendicular momenta of the particles, and that is essentially constant. So if I is a constant, then P perpendicular is going to be equal to I times B. So perpendicular squared is going to be equal to I times B. And if the particle is entering the region of stronger field, where the field lines are bunching up, so if the amplitude of B increases, then the transverse momentum squared is going to increase as well. It's proportional to B because the adiabatic invariant is roughly constant. And because P perpendicular increases, because total energy is conserved, we neglect the radiation and energy losses, then P parallel will have to go down. So eventually, if our magnetic field becomes strong enough such that P perpendicular squared reaches E squared, then P parallel will vanish. And that means that it will change sign and the particle will reflect. So that is a phenomenon of reflection off of regions of strong B. So how do we get to show that this is the expression for the adiabatic invariant? Well, not surprisingly, it comes from classical mechanics. Let's get to it in the next part 5 of lecture 22. Hello and welcome to part 5 of our last and awesome lecture 22. We continue talking about adiabatic invariants, and we just defined what adiabatic change means. It means that the variable that is externally imposed in our system is changing slowly compared to a period of our system. So in one period, the change of the variable is tiny compared to the variable itself. So suppose that our Hamiltonian depends on this externally imposed variable. So lambda enters the Hamiltonian, and if lambda depends on time, it means that the energy is not going to be conserved. So we're going to have to find some other variable that is going to be conserved, or the adiabatic invariant. So if energy is not conserved, let's write out the full time derivative of energy, or equivalently the full time derivative of the Hamiltonian, or equivalently, as we showed previously, this is equal to the partial derivative of the Hamiltonian, or equivalently, because the only dependence of the Hamiltonian on time is through lambda, it will be the partial of Hamiltonian with respect to lambda times d lambda dt. So let us now average this over a period of motion. Are we going to denote averages as horizontal bars? So the orbital average of d dt is going to be equal to the orbital average of d lambda dt, but because lambda changes so little in one orbit, we don't have to average it. We can just treat it as a constant times the partial of dh d lambda, which is averaged. So this very slowly. So in this term, the only things that vary are the coordinates. So we're going to be able to treat lambda over there as a constant. So let's formally write out what we mean by the orbital average. It will be an integral from 0 to the period of the period of the motion divided by the period itself, and here we're going to put the time integral of the quantity that we would like to average. And importantly, we can write out dt in the following way: dq divided by dh dp. Remember, it's q over q dot, right? So that will be delta t. And so we can continue this and write it out as d lambda dt times an integral over one period of dh d lambda times dq. Let me rewrite this so it's cleaner. Divided by dh dp. And all of that will be divided by the period, which will be just an integral of dt. dq over dh dp. So, as we mentioned, in these integrals over the period, we're going to treat lambda as a constant, which means that energy over one period we will treat as well as a constant, because then there's no time dependence in the Hamiltonian and it's going to be conserved. Which means that we can express the momentum as a function of the coordinate and the constants E and lambda. And we can plug this into the expression for Hamiltonian. Because energy is a constant within our approximation, by taking the derivative of both sides with respect to lambda, we're going to be able to write that 0 is equal to dh d lambda. That, on the other hand, is equal to the partial of h with respect to lambda plus dh dp partial times dp d lambda. And all of that is equal to 0. So from here, though, dh d lambda divided by dh dp is going to be equal to minus dp d lambda. Let us now take our awesome d dt expression and plug in that expression over here. We're going to get that the orbital average of d dt is equal to minus d lambda dt. The minus sign is coming from here, times the orbital average of dp d lambda times dq dq, and here we're going to have an orbital integral of dpd times dq. So you see that d lambda dt is migrating to here, and you also see that dh d lambda over dh dp is equal to minus dp d lambda, which is precisely the numerator. And then the denominator we can invert and take it from the denominator of denominator into the numerator of denominator, and we're going to get dh dp is equal to the inverse of dpd. So this plus that is giving us this. Let us now collect the terms and move over from here to, so we're going to multiply both sides by the denominator, and we're going to get that the integral over the period of dp dE times the orbital average of d dt plus dp d lambda times d lambda dt is going to be equal to 0. And on the other hand, this very much looks like simply an integral of dp dt, because p only depends on q, e, and lambda. So this is the full derivative. So from here we can immediately see that our adiabatic invariant is given by this integral, and that our adiabatic invariant is equal to 0, meaning that time derivative of the adiabatic invariant is equal to 0. So what is the adiabatic invariant? So let's write it out. I is equal to 1 over 2 pi. It's an arbitrary notation, but we're going to assume it, adopt it, just because we're following Landau and Lifshitz, times the integral over the orbit of p dq. So this is basically the area enclosed by the orbit. And this remains constant when lambda varies within our approximation. Note that this can also be written as an integral over the inside of the orbit, over the area of the orbit, of dp dq divided by 2 pi. If we multiply our adiabatic invariant by 2 pi, and take its derivative with respect to energy, then we're going to get and the following, and because dp dE is simply q dq divided by dq dt, so it will be dt. So all of this is going to be simply an integral of dt, and that is going to be simply the period of the orbit. And from this we can get that the inverse dE di is going to be the frequency of the system. That does it for section 5 of lecture 22. And in the next section, we're going to take a look at what this expression for the adiabatic invariant means for a charged particle moving in the magnetic field. And we will also start the discussion of the canonical variables, or the action angle variables. I'm going to see you in the next part, part 6 of lecture 22. Hello, and welcome to part 6 of lecture 22. So let us think, what about our charged particle in the magnetic field? What about the adiabatic invariant that we were after? So there, the adiabatic invariant is going to be given by the integral of p dq divided by 2 pi. So what is that? It's going to be 1 over 2 pi times the momentum of the particle, p perpendicular, times the length of the circle, 2 pi times the gyro radius. So 2 pi goes away, and we can plug in the expression for gyro radius into here, which will give us p perpendicular times c divided by qb. And this gives us p perpendicular squared over b times c divided by q. And this is the first adiabatic invariant. It can also be written as the magnetic moment. So with that, we're now done with the particle generating the magnetic field. We have obtained the expression for the adiabatic invariant that we started this discussion with, and we also have noticed that this adiabatic invariant is also called as a magnetic moment of a particle in the field. So let us now spend the remaining part of this lecture in discussing the canonical variables, or the action angle variables, or coordinates. This is chapter 50 in the 3rd edition of Landau and Lifshitz. So suppose that our system is closed, that is, our lambda adiabatic invariant, that our externally changing variable is actually not changing. So let us now switch to new variables using a canonical transformation, and let us take I, the adiabatic invariant, as the new momentum. So the generating function in this case, we can write down as S of QE and lambda, and that will be the integral of P of QE and lambda dq, so that when we take the partial derivative of S with respect to dq, the integral disappears. It's a running integral over the path, and we are going to get that ds of q e lambda dq is giving us p, which is precisely what we wanted from our generating function, right? D generating function dq should give us the original momentum, and that's exactly what this generating function does. So because we are treating the system as closed, if lambda is a constant, it means that there is no time dependence. It means that our energy is conserved. Because the adiabatic invariant is a function of energy and lambda, if both energy and lambda are constants, that means that our adiabatic invariant is also a constant, and therefore the partial derivative of ds dq under e equals to constant will be equal to the partial derivative ds dq under I that's equal to constant. And from here we're going to get that this is equal to ds dq of q, I, and lambda. That is giving us our p. So indeed, the partial derivative of our generating function with respect to q under the constancy of our new momentum I is giving us the original momentum, which is indeed the confirmation that our generating function is doing exactly what we wanted to do. So as a result, we can say that the transformation from q and p to I and whatever other variable will be, this will be the new coordinate, is going to be the right one, and w, the new coordinate, is going to be the partial of s with respect to our new momentum. So new coordinate is partial of s with respect to the new momentum. So these are canonical variables. I is known as action variable or coordinate, and w is the angle variable. Under our canonical transformation from q and p into w and I, we made an assumption that our transformation doesn't depend on time because lambda is a constant. That means that our new Hamiltonian is equal to the old Hamiltonian because there is no time dependence in our generating function. Thus we can write down Hamilton's equations in canonical variables. I dot is equal to minus dh prime dq, or dh dq because h is equal to h prime, is equal to minus dE dq. And because E only depends on I, therefore we have shown that our adiabatic invariant is indeed going to be invariant. It doesn't change in time. Similarly, W dot is equal to dE dI, and this will be giving us the solution for W, which is the partial of energy with respect to momentum times time plus a constant. Or equivalently, omega times time plus a constant. You might wonder, why is our omega a constant? Well, that's because this this derivative only depends on I, and I within our approximation is a constant. So that's precisely why we can treat omega dot as a constant integrated straight up. So this W is the phase of the oscillations. So one important aspect of all this is that our function S of Q and I is multi-valued. It increases each period. So let us find the increment of S over the period. That will be simply 2 pi times I. That is because I is equal to the integral over the period of p dq, which is precisely what will be the value of S after one period. So that is what sets delta S. Finally, the increment of W over the period will be equal to delta W, or delta of ds di and that is because of the definition of W ds di, right? And we can flip the order over here. It will be d di of delta S, and delta S is just 2 pi I, so this will be simply 2 pi. So you can see indeed that W is the phase of the oscillation. With this, we have wrapped up our series of lectures in our course of classical mechanics. I hope this was a lot of fun, and we have figured it out what is going to be conserved when almost nothing is supposed to be conserved. When there is a slow variation of an externally imposed parameter in our system. We figured out what the adiabatic invariant is, we've derived it, and then we have introduced the canonical action angle variables, which are so convenient. One of them is not changing, that's an adiabatic invariant, and the other one is the phase of the oscillation. One thing that I want to mention at the end is that here we made an assumption that lambda was a constant, and then we have been able to obtain all of these variables. However, you can relax this assumption, and this is what Landau and Lifshitz does in the next paragraph, where they relax this assumption and then are able to evaluate the accuracy to within which the adiabatic invariant is conserved. So that's something that you can check out if you're interested. Thanks so much for your attention. I hope it was as much fun for you as it was for me, and I'm going to see you around. Have a lot of fun and a wonderful break. Bye.